Section 9.1, Systems of Linear Equations with Two Variables. In this section, we'll solve systems of equations by graphing, by substitution, and by addition. We'll identify inconsistent systems of equations, and we'll express a solution of a system of dependent equations containing two variables. So a system of equations are two or more equations made up of two or more variables whose solutions are considered simultaneously. So in other words, we're looking for the solution which makes all of the equations true at the same time. The three methods of solution are graphing, substitution, and addition, and sometimes addition is also called elimination. Everything in this section you've done before, many times in almost every algebra class you've ever taken. So there's nothing today that we're going to do that's anything new. We're just going to remind you of how this works. Of these three ways, graphing is the worst way to go, because in order to solve a system of equations by graphing, you have to have a sheet of graph paper, you have to be very neat, and you have to have a solution that crosses your graph at a lattice point, meaning at a point where the x and y coordinate are whole numbers, which often doesn't happen. So I'm not even going to cover that method because it is so limited. But we will cover substitution and addition elimination. First thing, do all systems of linear systems have solutions? Well, in this first picture, we have a red line and a blue line that cross in one point. And so it's possible that a system of equations has one solution, one value for x and one value for y. It might be that the lines are parallel, meaning there are no points that make both equations true at the same time. And in this case, we have no solution. And a system like that is called inconsistent. And so one of the things we'll need to talk about is how you recognize an inconsistent system. And the third thing that can happen when you have a system of linear equations is that both lines could coincide. So when the lines coincide, there are an infinite number of solutions. Everything that is a solution for the first line is also a solution for the second line. And in this case, this system is called a dependent system. So let's review solving a system by substitution. So basically, these are the three steps you're going to follow. You're going to solve one equation for one of the variables. You're going to substitute this value into the other equation, creating an equation with one variable that you can solve. And then you'll solve for the remaining variable. So here's an example. So to solve this system, I'm going to solve this first equation for y. So I'm going to get y by itself. All right, so let's go ahead and take a look. So the first step is we have to solve one equation for one of the variables. So I'm going to take this first equation, negative x plus y is equal to negative 5, and I'm going to solve it for y, meaning I'm going to get y by itself. So that means I'm going to add x to each side, and that will tell me that y is equal to x minus 5. And then the next thing we're going to do is we're going to substitute that into the other equation. So this is the other equation, 2x minus 5y is equal to 1. And so y is equal to x minus 5. So in this equation, I'm going to replace y with x minus 5. So if we do that, we have 2x minus 5. We're replacing y with x minus 5 is equal to 1. So this gives us an equation with one variable that we can now solve, and we'll go ahead and do that. 2x minus 5x plus 25 is equal to 1, negative 3x, and I'm just going to do this in one step. I'll subtract 25 from each side. Negative 3x is equal to negative 24, and dividing by 3, we find out x is equal to 8. Once we know that x is equal to 8, we have to solve for y. We can put 8 in for any value of x anywhere we see it, an x, but the easiest place is to put it right here. And so y is equal to 8 minus 5, or in other words, y is equal to 3. So this system has one solution. X is equal to 8, y is equal to 3. In other words, if we were to graph these lines, they would intersect at the point 8, 3. Let's do another example. X minus y is equal to 3, and 4 is equal to 3x minus 2y. So I'm going to take this first equation, x minus y is equal to 3, and I'm going to solve it for x. So to solve it for x, I'm going to add y to each side, and that will tell me that x is equal to y plus 3. Now this is the second equation. This is the other equation. And so what I'm going to do is I'm going to take this value and I'm going to replace it for x in the other equation. That tells us that 4 is equal to 3 times, I'm replacing x with y plus 3, is minus 2y. This has an equation with one variable, which we can solve. 4 is equal to 3y plus 9 minus 2y. 4 is equal to y plus 9. Subtracting 9 from each side, we'll find out that y is equal to negative 5. And again, we can replace negative 5 in for y anywhere we see an equation, but the easiest place would be right here. So x is equal to negative 5 plus 3. In other words, x is equal to negative 2. So were we to graph these lines, they would intersect at the point negative 2, negative 5. Here's one for you to try. Well, before you start that, let's just talk about how you make this first selection. When it says to solve one of the equations for one of the variables, always pick an easy variable to solve for. So what are we looking for? We're looking for a variable that does not have a coefficient that's not 1. So easy variables to solve for in the first system would be this x or y. In the second system would be this x or this y. The reason those are easy is because if there's a coefficient that's not 1, to solve for that variable you would have to divide, which can sometimes introduce fractions to your work. So on this one that you're about to do, the only variable that's easy to solve there is this y right here. So why don't you go ahead and try that.